Morning. I am Jill Higginson. I'm a professor in mechanical and biomedical engineering at the University of Delaware, where I also serve as the associate director for the Delaware Rehabilitation Institute. Today, I wanted to thank you for the opportunity to provide a quick overview of our work, which is in the Neuromuscular Biomechanics lab, where we are trying to address problems in rehabilitation science. So in general, I'm interested in how the brain controls movement, and more specifically, how muscles are coordinated in normal neurological systems in order to produce movements that are desired. My expertise is in musculoskeletal modeling, and so I use these computational models to develop a cause and effect framework that ultimately, we hope to relate muscle impairments that we can observe in the models to deviations, often in gait. The nice thing about using a computational model is it allows you to ask what if scenarios or perform experiments that you can't perform on human subjects. And this allows us to form a scientific rationale for some of the therapeutic interventions that have been designed to improve movements. So, most of what we study is gait, and in order to build good models of the musculoskeletal system, we need really clean experimental data, so we also run a motion capture lab. And so this involves full body kinematics and kinetics that are captured while we're moving. We also are interested in interactions between the muscle function and cognitive function. So we're looking at whether, performing multiple tasks at the same time interrupts movement. And with collaborators like Eric Thostenson and others, we've been exploring the use of devices to aid movement. So our work has really kind of changed a little bit and evolved over the years, which is really a fun thing about being in the university community. So I think I said most of what I like to study is gait, and I'll start there. I gave a talk a year or so ago, which I called 100 Ways to Use a Treadmill. And that really does kind of capture most of the things that we're doing in the lab. We use a treadmill for all sorts of different studies and populations. We often are studying healthy young adults to look at what are the normal movement patterns and what changes when we intervene on their system. Over the years, we've conducted a number of studies that include a study shown on the top left. The collaborators on the COBRI project are shown, and we studied knee osteoarthritis. So my component of this study was to look at changes in walking kinematics and whether there might be early predictors to movement and development of knee arthritis in stages 0 through 4 of arthritis. But for the most part, over the last 15, 16 years, we've been studying stroke. And we've done this through a variety of different studies. The one in the top right is our FAST FES study, which was a 12-week intervention study on individuals who had suffered a stroke, where we asked stroke survivors to walk on a treadmill at a speed faster than what they were normally comfortable at, as well as applying functional electrical stimulation to the muscles of their lower leg. And this ended up being remarkably effective at enabling them to control and improve the function of their muscles and achieve faster walking speeds. In related studies, we've done some robotic exoskeleton work, again with another series of collaborators, initially with the ALEX studies and currently with the GOAL studies. And what we've done here is use an exoskeleton in order to specifically intervene on specific leg trajectories while a stroke survivor is walking. And the intent is to enable the stroke survivor to achieve multiple iterations of movement while getting the level of assistance that a therapist might be able to provide. So again, both of these studies have been effective at improving the gait patterns, but also teaching us a bit about how best to intervene for stroke survivors. And then you'll see the little model in the lower right-hand side. We've used a lot of this gait data, the experimental data, to build subject-specific models of these individuals to look specifically at impairments that we see in specific muscles and how this changes with different interventions and how certain muscles are responsible for certain impairments that we see. One of the limitations of the treadmill, the traditional treadmill, is that it's typically limited to a fixed speed. So the subject comes in and is walking at a comfortable speed, and then we intervene on their movement, but they're still stuck at that same speed. So we spent some time over the last couple of years developing a user-driven treadmill. And this one is, let's start the video here. This one is sort of as described. It's a self-paced treadmill such that you can increase the walking speed by moving forward on the treadmill, by increasing your push-off forces, or by increasing your step length. And then it resolves to a steady state speed. Or you can reduce your walking speed by falling a little bit back on the treadmill and decreasing your step length or decreasing your push-off forces, and then you can maintain that steady state walking speed. So the nice thing about having this kind of flexibility in a system, well, not only does it allow you to change speed sort of on demand, but it also allows you to have more natural stride-to-stride variability, which is typical with overground walking. And also, this kind of variability is known to enhance learning, especially if you're going to intervene on someone's movement. So again, this tool is really useful for introducing interventions in real time. So the idea is now we can apply functional electrical stimulation or a robotic exoskeleton and allow the individual to modify their movement in real time to see whether or not this type of intervention might be effective. So we've done this on a series of stroke survivors and healthy young adults, and in both cases we see marked improvements in their walking speed and their walking kinematics instantly, which is really interesting when you compare to a study like the FAST-FES study, which took 12 weeks to see changes in walking speed. And now within the course of a single session, we can see an increase in sustainable walking speed. So we're pretty excited about this as a potential for future therapeutic interventions, and we are hoping to develop this into a longitudinal study. So here's a shameless plug. This is primarily the work of my PhD student, Nicole Ray, who is scheduled to defend 2 weeks from today on Star Campus in the North Atrium, and all are invited to attend the open session, which starts at 9 o'clock if you are so inclined. So now, shifting gears completely. Most of our work does involve gait and stroke. However, with an interdisciplinary set of collaborators, we are working towards a new vision of wearable technologies. And you might have heard a little bit about this a few weeks ago with Eric Thostenson, but we've developed this collaborative team to target upper extremity shoulder assistance with a program we call HENSWare, but it's designing wearables that are both functional and fashionable, and it includes multiple components. So in order to target upper extremity shoulder assistance, it's important that we include elements of support, that we include sensors to detect movements, that we integrate this technology with textiles in order to, again, promote the function and the wearability for a specific user. And ultimately, the user, we hope, will learn and adapt to this system. And the feedback that the system is able to provide, this could be provided to the user and or the clinician in order to monitor progress and changes in performance. So my role here is in human-garment interaction. I'm really most interested in what's the level of muscle effort required in order to achieve upper extremity movements. How is this assisted by a supportive device? What kinds of muscular effort can be offloaded or replaced by this type of system? And then specifically related to the design of the garment, what kinds of attachment points might be relative? As you can see on the right-hand side, the shoulder musculature is quite complex, and we can imagine that a synthetic system is not going to include nearly so many attachment points. So what are the appropriate muscles to augment, where to provide these attachment points, how best to generate force transmission, and ultimately, what is the design of a system that promotes optimal form and function of a wearable garment. So this work is really just getting started. We're pretty excited about it, and so I'm going to give another shameless plug about our first annual Henswear Symposium, which is scheduled for tomorrow. And it's on the Star campus. It includes a really nice agenda that includes a whole series of lightning talks in the morning and the afternoon. And there's a keynote lecture by Lucy Dunn, who is an expert in wearable technologies from the University of Minnesota. So all are welcome to attend. If you want food, you should register. Okay. So that's my quick overview. Our work is currently supported by these sites. It's really broad reaching at this point, everything from healthy and pathological movement to gait and upper extremity movements. And so I'm happy to answer any questions that you might have.